Good afternoon, everybody. I'm Narayana, and this is my advisor, Pat Arnold, here at the back. And I'm talking about the thermal infrared, long-wave radiative forcing by atmospheric air. So let me start with some basic definitions. Aerosols, I mean the atmospheric aerosols, are the tiny solid and liquid particles suspended in the air, and their sizes range from nanometers to few micrometers. Out of several examples of the aerosols, my study mainly focused on biomass burning smoke and airborne mineral dust aerosols. And the aerosol optical depth, AOD, is a measure of total scattering and absorption by aerosols. Radiative flux is the radiative power incident on unit area. And the aerosol radiative forcing, which is a very important term in that talk, is measured as the difference between the radiative flux with aerosols and radiative flux without aerosols. And keep in mind, these both quantities are measured in terms of watts per square meter. Now I'll briefly explain how aerosols affect climate. And I took this information from IPCC, Intergovernmental Panel on Climate Change, report 2030. Aerosols scatter the incoming radiations leading to the cooling event. Also, some aerosols absorb incoming radiation leading to the warming effect. And these two effects are called the direct effect of aerosols on the climate. Aerosols also affect the climate indirectly by serving as a cloud condensation nuclei, allowing the formation of cloud. Maybe you might know cloud has a big impact on the Earth radiative budget. This chart displays the radiative forcing due to various components present in the Earth atmosphere system over the period 1750 to 2005. Out of these several components, let me focus on this aerosol forcing right here. This is the aerosol forcing. Keep in mind, this is just a short wave aerosol forcing. And negative sign indicates the aerosol has cooling effect. Here, my question is, what about the long wave aerosol forcing? Remember, the climate models do not take that particular quantity into account, assuming that this is negligible. Our concern is this quantity really small or small enough to be ignored? So that's the objective of our research. And the objective is fulfilled by analyzing two case studies. Smoke and the dust storm events that took place in Reno last year, 2030. Reno observed a huge smoke during August and September last year from the California rimfire. And this rimfire was the largest wildfire in California's recorded history. This satellite image shows the flow of huge smoke plume toward Reno all the way from the rimfire site. The picture on the bottom shows the smoke haze hanging over Reno, and the visibility is highly reduced. These are the aerosol size distributions observed during the smoke and the dust storm event. This is smoke event, this is the dust storm event. And the side distribution consists of two modes, fine mode and coarse mode in this case. And remember, the fine mode consists of the particles about less than 1 micron, and the coarse mode are the particles greater than 1 micron. Now we see that during smoke event, fine mode heavily dominates over the coarse mode. But during the storm event, dust storm event, the coarse mode heavily dominates over the fine mode. Now we use those informations, including the spectral complex refractive index and the aerosol optical depth to derive the single scattering properties of these different modes of aerosol, and we compute and we input those things into the radiative transfer model to compute the radiative forcing. These are the spectral radiative forcing due to various modes of aerosol during the smoke event. This is the bottom of atmosphere aerosol forcing, and this is the top of atmosphere radiative aerosol forcing. It is obvious that both the BOA and TOA forcings are much stronger in that region, which we call the infrared window region, which lies in the 800 to 1300 inverse centimeter, or 8 to 20 micron. But in the rest part of the spectrum, these values are very, very small due to the strong absorption band of gases. Also, the BOA forcing in magnitude is much larger than the TOA forcing. And again, the fine mode forcing, the black line, is larger than the coarse mode forcing, this is the red one, and this is because the fine mode concentration is higher than the coarse mode concentration. Now, look at the dust event. We see very similar features in the dust case. In this case, the coarse mode forcing is much larger than the fine mode forcing in this case. Next, we compute the broadband radiative forcing over the 5 to 20 micron range by integrating the spectral flux. This term is the spectral flux. And these are the BOA forcing and these are the TOA forcing for different modes for the smoke event. We are interested in these values because the smoke particles lie in the fine mode. Now the question is, are these values big or small? If you say big or if you say small, are they really negligible? So let me answer that question based upon a fact taken from IPCC report 2007. What it says: the TOA radiative forcing due to increase in CO2 concentration in more than 250 years is just plus 1.6 watt per square meter. And you know the climate scientists are most worried about that number to the consequence of the global warming. So as compared to that number, our values are not small. Even if you say small, these are not negligible. Let's look at the dust event and the coarse mode forcing. The question is again, are these values big or small? So from the long wave forcing perspective, these values are really huge and significant. Now conclusion, the long wave radiative forcing by the fine mode smoke aerosol usually at high concentration is positive and non-negligible. The long wave radiative forcing due to coarse mode neutral dust aerosol is significant and positive. So what is the impact of those things? The aerosol long wave radiative forcing therefore produces warming effect. The positive signs indicate the warming effect and contributes to the partial counterbalance the well-known strong aerosol cooling effect in the southern region. Our results of radiating forcing for the dust case are consistent with the recently published results of the Sticard and others in 2014. Our findings underscore the importance of inclusion of accurate aerosol longer radiative forcing in climate models to complete it. Finally, thank you.
Eruptions can cause long-range changes in weather patterns, sometimes lasting several years. So that's dust.
Yeah, that's dust.
Yeah. So you did some studies on dust.
Yes.
How does the force in your find compare with the historical data on volcanic eruptions?
Yeah, we actually did not compare those things with the volcanic kind of dust. This is the kind of desert dust we studied about.
Right.
And then maybe there can be different in their composition, chemical composition, and we need to use a different impact index, and then we need to figure out how it is different from the volcanic origin dust.
So the sulfuric acid droplets that get pushed into the stratosphere under a big eruption push the solar radiation away for a couple of years, and that's the primary effect. The ash left effect.
Yeah, could you go back? For the entire column, or it's going to differ?
Yeah, it is assumed to be uniformly distributed,
Okay.
but it may not be true.
Okay.
Okay, so our last speaker is Sandra